Find the area of the regions bounded by f of x equals 5x minus x squared and g of x equals x on the interval 0 to 5. A graph would definitely help in this case, and so at first, always draw the graph. If it is too difficult to draw the graph, at least find the intersections of the two by setting them equal to each other. Solving this equation using the zero product property, we have x equal to 0 and x equals 4. These are the two locations where f and g change their positions from upper to lower. We are only interested in the interval 0 to 5. Between 0 to 5, we found two zeros for the equation 5x minus x squared equals x. We then determine which function represents the upper curve and which function represents the lower curve in each of the subinterval. To do this, we pick any arbitrary number in each subinterval. For example, we pick x equals 1 and we evaluate f when x equals 1. f of 1 is 5 times 1 minus 1 squared, which is 4. g of 1 is 1. And so at x equals 1, f of 1 is 4 and g of 1 is 1. 4 is definitely greater than 1. On the interval 0 to 4, it must be true that f of x is greater than g of x, meaning f is the upper curve and g is the lower curve. We do the same thing for the second subinterval. Pick any number inside this interval, 4.5 for example. f of 4.5 is 5 times 4.5 minus 4.5 squared. Both of the terms have factor 4.5, so we factor out 4.5. 4.5 times the quantity 5 minus 4.5, which is 4.5 times 0.5. This is 2.25. g of 4.5 is 4.5. 4.5 is greater than 2.25, meaning g of 4.5 is greater than f of 4.5. So on the interval 4, 5, the function g is the upper curve. And so on each of these subintervals, we will set up the integral using the upper curve minus the lower curve. We will obtain two areas. The first area, a sub 1, is the integral from 0 to 4. The upper curve is f, so 5x minus x squared, minus the lower curve is x dx. The second area is the definite integral from 4 to 5. The upper curve is g of x, and so x, minus the lower curve is 5x minus x squared dx. We then use the fundamental theorem of calculus to evaluate each of these integrals at the two areas to obtain the total area. The first area is 32 over 3, and the second area is 7 over 3. The total area is therefore 39 over 3. When evaluating each of these integrals, make sure to simplify the integrand, find the antiderivative, and use the fundamental theorem of calculus to evaluate the definite integral.